Thank you, thank you. You know, this is exciting. I've never been to a meeting where I had no idea how we were going to get there from here, because I have no idea how we're going to measure magnetic fields on planets, but I hope to find out today, or this week. It's not that we haven't thought about this, but I just have. I'm completely mystified as to what we're going to do. So this will be a learning experience. Okay, so the first speaker this morning prepared what I believe is a beautiful talk, but he's not here, and Gerald Schubert is the preparer. If he had been here, I would have told you the way I first learned about him, which was when back many years ago, when we were doing an experiment at the CFA and looking at Venus and measuring the CO2 lines on Venus, and had heard that the upper atmosphere of Venus was rotating, and so we used our high-resolution spectrometer to measure the Doppler shift on the left and the right sides of the image of Venus, and tried to measure something which turned out to be about 100 meters per second stratospheric wind. And Gerald Schubert was one of the people who came up with explanations as to why the atmosphere of a essentially non-rotating planet ought to be zipping around in a given direction and systematically. So, you know, maybe I'll hear more about that during the talk this morning. However, Professor Schubert is occupied. I can't be here, and Dave Stevenson has stepped in to agree to give his talk, and I think at that I should just let you take over, okay?
Jerry has a family medical issue he has to deal with. And I have had his slides for a couple of days. They actually overlap to a significant extent with the material I was preparing, so it was not too difficult to go through his slides and understand what he had on them. What is going to happen is that I will go through his talk, but of course I'm not working from a script, so what I say as the slides go up will be a little bit different from what Jerry would have said, hopefully with no contradictions. And the way I have structured it is that my talk, which follows, will be more theoretical. It will talk about the challenges in dynamo theory, the challenges in understanding the thermal evolution of planets. These are the central challenges in any attempt to understand magnetic fields, what we see, and what we might see in exoplanets. So let's get underway and begin with the obvious comment that magnetic fields are everywhere. They are ubiquitous in the universe, and they are found throughout our solar system. The prevalence of magnetic fields is traceable to the prevalence of free charges, and of course when you have charges in motion, you have currents, and from Ampere's law you have a magnetic field. And in fact, all of the planets, with the possible exception of Venus, have or have had magnetic fields. That's a remarkable statement, and you could argue that the absence of a field associated with Venus is just a consequence of the fact that its surface is so hot and so it can't retain a memory. My guess would be that in fact Venus did have a magnetic field, but it doesn't have one now. Remarkably, if you look around our solar system, even moons and small bodies have or have had magnetic fields. Ganymede is generating a magnetic field. Vesta and Gaspra in the asteroid belt are examples of bodies that have evidence of a previous generation of a magnetic field. So you can see that this is a very common phenomenon. And of course they're of interest for many reasons, but one of the reasons that we want to study planetary magnetic fields, certainly the reason why I chose to, is because I believe that you can use this as a window to understanding the interior properties. Magnetic field is in fact the only remote method, the only remote probe of the deep interior dynamics. You can use gravity to talk about structure, but the magnetic field, we believe, comes from a dynamic process, and so it tells you a certain kind of unique information that you can't get any other way. And of course, it affects the exterior. It provides a shielding of the planetary atmosphere, and therefore the presence or absence of a magnetic field is relevant to habitability. One of the things that you're going to see in my presentation, both talks, is a common theme, an emerging theme, which is that this is a subject where our understanding is poor. We don't really have a very good understanding of magnetic fields, their generation, the criteria for having a magnetic field, and this will come up time and again as we go through the two presentations. But first, a few words about how you measure magnetic fields. The most common way is through use of magnetometers. Magnetometers measure flux, basically, and therefore you have to be there. You have to send a spacecraft to the planet, and the planet has a magnetosphere, and so you can see the presence of that local magnetic field in the region where it overwhelms the presence of the solar wind. And so we have, of course, sent the spacecraft to all of the planets, and we have done that measurement. And that is our main data set. The other thing that you can do in situ is use electron reflectometers, which are telling you about the trajectory of electrons in the magnetic field. And this is useful close up. So if you have a spacecraft in a tight orbit, for example, around the Moon or around Mars, then you can learn more about the detailed structure of the magnetic field near the surface of the body. And so this has been done in a couple of missions, Lunar Prospector and Mars Global Surveyor. Of course, for this workshop, one of the primary questions is going to be the extent to which you can learn about magnetic fields without going there, that is, exoplanets. And what we do know in our own solar system is that electron cyclotron emission is, in fact, something that has been detected from all the gas giants and indeed from Earth. So if you go out in space and look back at Earth, you can tell that Earth has a magnetic field. And presumably, this is one of the issues that will get talked about more. Perhaps Greg Hallinan will talk about it more, the extent to which we can hope to do this or are doing this for exoplanets. The other thing, of course, which is indirect, doesn't tell you much about the geometry of the field or the magnitude of the field, but the presence of the field is revealed by the UV emission from planetary auroral regions, and this is in common with the observations for the electron cyclotron emission, the radio emission. Of course, there are some special cases. Jupiter is a special case. It has synchrotron emission, relativistic electrons, and Jupiter, of course, is the strongest radio source in the night sky. The other thing that you might do, and there are papers on this in the literature, suggestions about this, is that you can look at the transit light curve for exoplanets and see whether there's evidence for the bow shock caused by the magnetosphere, and this would be specific to hot Jupiters. But most of what goes on in this presentation will deal with data obtained by magnetometers, which means spacecraft measuring in situ. So we're going to do a tour of the solar system starting from the inside out, and we will start with Mercury. Mercury is the planet closest to the Sun. It is iron-rich. We know that it has a core that is primarily iron, part of which is liquid. We know that actually from ground-based observations, and we know about the magnetic field first in a preliminary way from Mariner 10 back in the 70s, and now from the Messenger spacecraft, which has collected detailed data. And the best way to talk about it is to show you a map of the magnitude of the field. So here, color-coded is the magnitude of the field, not the vector, so this is just the magnitude. There are three striking things about this figure. Rotation axis is like so. And so the three striking things are, number one, that the field is very axisymmetric. There's very little variation with longitude. Number two, the field is much stronger near the North Pole than near the South. And number three, these magnitudes here are a couple of orders of magnitude smaller than Earth's magnetic field. In fact, the field of Mercury is so small that until MESSENGER gave us new data, there were many of us who doubted that Mercury was generating a magnetic field the way the Earth does, that is, by a dynamo process. But now we think, because of the nature of this field, that it is likely to be a dynamo process, although you could argue that you can really only be sure if you see time variation, because a dynamo is a dynamic process, and so the real smoking gun for a dynamo is the change of the field, which is the strongest argument in the case of the Earth, by the way, and was already noticed by Edmund Halley back in the 1600s, the same guy who found Halley's Comet. But anyway, to get back to the observations, the smallness of the field is actually a puzzle. We do not know why Mercury is so inefficient, if you will, in generating the field, and it's a warning about any sort of generalization that you might get from the theory that we have for making magnetic fields. When you see the field concentrated spatially like this, your first temptation is to think, oh, somehow or other there's an asymmetry in the planet. Somehow the northern part of the planet is different from the south. But actually, dynamo theory gives you this kind of symmetry breaking. It can give you a quadrupole, which is really what this represents. You can think of it as an offset dipole, but that's the same thing as talking about an axial quadrupole. And so dynamo theory is in principle capable of explaining this, but it is quite startling. The axisymmetry is, again, a property of the dynamo. The field cannot be perfectly axisymmetric. There's a fundamental theorem called Cowling's theorem that says you can't do that, but the field is, in fact, not perfectly axisymmetric. It's just close to it. And this may be a testament to the nature of the flows in the interior, perhaps a stable layer at the top of the core. There are many ideas for why that might be so. And so here Jerry has listed the questions, the same things that I have just mentioned. And I'm not going to go into the detail of the various models that have been suggested, but suffice to say that there has been a lot of work, some of which involving conducting stable layers, some of which involving the fact that the field is generated in a thin layer, but maybe even in a thick layer. There are many different outcomes that you can get from dynamo theory. And by the way, this is one of the problems with dynamo theory, that it can produce too many different answers. And so it's hard to decide a priori what the correct story is. But one of the things that is of interest in the case of Mercury is that because it's a small planet compared to the Earth, the regime, the phase diagram of relevant to the core, has different properties than in the case of the Earth. And if you thought the core was sulfur-rich, we don't know that, but if you thought it was, then there are some interesting possibilities involving snow both upwards and downwards. This represents iron particles which sink. This represents FeS particles which rise. And this produces a distribution of buoyancy that could affect the way the magnetic field is produced. One other thing of interest in the case of Mercury and of relevance for thinking about exoplanets is, of course, that Mercury is a body with a small intrinsic field, but sitting in the presence of the material from the sun, and the magnetosphere is affecting the current distribution external to the planet, and therefore affecting the magnetic fields that you measure. And there is a feedback, a generation of magnetic fields externally in the magnetosphere that tends to weaken the overall field. So the message here is that when you look at a planet from afar and infer something about magnetic fields, you have to keep in mind that sometimes it's not the intrinsic field that's giving you your observation, it may be modified by the external field. And of course, the extreme case of that is the Galilean satellite sitting in the magnetosphere of Jupiter. Jupiter has an immense magnetosphere, and the magnetic fields are greatly altered and in many cases dominated by Jupiter rather than by the satellite. Now, there's no slide about Venus, and that's because Venus has no global field, and that's an interesting question that I will come back to because Venus is in many respects similar to the Earth. But we have no observed field for Venus, and there is no slide in Jerry's set of slides about the Earth. I will say something about the Earth in my presentation. We jump now to the Moon. So the Moon has no global magnetic field, but it has magnetic anomalies. So here you see latitude, longitude, and these anomalies on the surface, and these can be measured by a nearby spacecraft, and also one can learn something about the magnetization. This is permanent magnetization in surface material, actually metallic iron. In the rocks, you can learn about that also by looking at lunar rocks. So these are isolated anomalies. They're small, and in some cases they're associated with impact features. Now, the interesting thing about the Moon is this, that we have difficulty understanding what we see except by saying that the Moon once had a dynamo. So we think that the Moon once had the same thing that the Earth does and that Mercury currently has, and that it operated actually for a significant period of time, because we see the evidence for the magnetic field in rocks spanning a period of time of about 600 million years. Ben Weiss and people working with him at MIT have been carefully documenting this in recent papers, and so we think that the Moon actually had a fairly large field, large at the core. The Moon is a body whose composition is similar to Earth's mantle, but it has a small core, perhaps 300 or 400 kilometers in radius, which is small, of course, compared to the surface. And because of the inverse cube drop-off of the magnetic field as you go away from the core, that means that if you infer something at the surface, you have to take into account that inverse cube behavior to get an estimate of the field in the core. And it turns out that the fields in the core are similar or even larger than Earth's magnetic field, which is startling. It's also startling that the Moon was able to do this for quite a period of time. It's difficult to do this by thermal convection, which is a popular idea for generating magnetic fields. One alternative, which I was involved in, is precession. It turns out that the core does not follow the precession of the mantle, which is happening on an 18.6-year time scale, and so you have differential motion between the core and the mantle, and that can set up flow which will generate a magnetic field. This is, if you will, a flow similar to what happens in a washing machine. In a washing machine, you set up by mechanical stirring a flow which in fact has a chaotic character, and so I often use a washing machine as an example of how dynamos can work, because the flow in a washing machine is actually a very good one for generating a magnetic field. If this story is correct, then it's tied to the history of the orbit. The amount of power that's available to generate the lunar magnetic field is tied up with the question of how quickly the Moon moved away from the Earth and what the timescale was for the precession during that period. It's also possible to generate a magnetic field transiently in the Moon, in the core, by impact. So what happens is you hit the Moon, and the Moon, which is normally just librating like so, if you hit it hard enough, will actually start rotating and then will spin down back into its current libration state with one face towards the Earth. And during that period, you might generate a magnetic field, but it's difficult to see how that story would work for many hundreds of millions of years. One of the other interesting points is that the material that is magnetized is close to impact basins, and we see this here in Mark Wixowitz's slide, in adjacent region to South Pole Aiken, and he has suggested, others have suggested that it might help that some of the material that has been magnetized is actually delivered in the impact so that you can get higher magnetization. But the main issue with the moon, possibly the biggest puzzle among planetary bodies, is how to have the dynamo work for many hundreds of millions of years. And it could be that the moon is special. That is, uses a different mechanism than the other bodies. Mars does not have a magnetic field at present. In that sense, it is like the moon, but it has these magnetic lineations. So this is permanent magnetism in the surface material that you see when you have a spacecraft come within 100 kilometers or so of the surface. And again, this means that there must have been an active dynamo early in its history, and there's a great deal of debate about the length of time over which that dynamo was operating. And so here, Jerry is listing some of the ideas about that. My view on the situation with Mars is, to put it bluntly, we don't know enough. We have to go back there. We have to characterize the magnetic field better. That's not easy to do. That's something that I hope will be done some point in the future. Obviously, you want dating as well. We don't have real dating for Mars. One would hope that there is some way of doing that in situ, rather than the extremely difficult business of bringing back a representative set of samples to the Earth, although people want to do that as well. Of course, that's in the Planetary Decadal Survey. Let's move now on to the Jupiter system and to what is perhaps one of the most remarkable things, which is that we have a moon that does what Earth does, that is, generate a magnetic field by a dynamo. So here we have Ganymede, which of course is about half ice, half rock. This blue is not water, it's ice. This region in here is silicate metal, and then right at the center is a small iron core. And this body, which is of course larger than Mercury, but has a core that is considerably smaller than Mercury, is generating a substantial magnetic field. In fact, substantially more than what Mercury does. So this is a body that is capable of doing a better job in generating magnetic field than Mercury. And this is the best example we have so far of the lower bound, if you will, for making a dynamo at the present day. Ganymede is doing a good job right now producing a substantial magnetic field. The field, by the way, is anti-parallel to the rotation axis, and it's directed opposite to the Jovian magnetic field, and that means that the magnetic field lines link up. So here we see a description of the magnetic field geometry. Out here, of course, we have Jupiter's magnetic field, and here we have the field lines that are associated with the dynamo within Ganymede. And of course, this was mapped partially by the Galileo spacecraft. So this is how we know about these data and know about the presence of the magnetic field and know about its geometry. So why would it be that a body like this can do this, whereas a much larger body like Mars cannot currently do it? Well, again, I'm not going to go through the details, but probably an important part of the story is that Ganymede is volatile rich. It probably has a core that has much more sulfur in it than Mars has. This certainly gives you a phase diagram where you can get compositional buoyancy. As the core starts to freeze, you can get snow, you can get material raining out, which promotes convection, compositionally driven convection. And in this way, you can keep the system going. But it is nonetheless, at this point, unclear why Ganymede, among the satellites, does this, whereas, for example, Titan does not. You might have thought that Titan is somewhat like Ganymede. There are some very interesting questions about the extent of differentiation in these bodies. We're not sure that Titan is fully differentiated. We are pretty sure that Ganymede is differentiated. That comes from the gravity data. But there are some puzzles at the moment. Why is Ganymede doing this? Why doesn't Callisto do it? Why doesn't Titan do it? So Ganymede is striking in its special ability to generate a magnetic field despite its smallness and to keep doing it. And now we come to Jupiter, which of course is the body with the largest magnetic field in the solar system among the planets, and of course it is the largest planet, so it has a very large dipole moment. Field at the surface about 4 Gauss or so, and here is a map of the magnetic field at the surface. Jupiter is a body whose deep interior is dominated by metallic hydrogen. And so that material, which is in its fluid form, is ideal for generating a magnetic field, perhaps even out beyond the region which is metallic. Because it turns out, and I will come back to this later, that having high electrical conductivity is not really that necessary. In fact, not even desirable. Yes, you need electrical conductivity, but you don't need a really high value. You don't need a good metal. But Jupiter certainly has that in abundance, and we're going to learn a lot more about this magnetic field geometry with the Juno spacecraft, which will arrive there in 2016, and will determine the magnetic field of Jupiter to greater precision than we have for the internal field of the Earth. That's a startling thing, but it's true. Juno is going to do better than what we know for the Earth. So that's going to be very exciting for understanding dynamos and for understanding the dynamics associated with magnetic fields. The tilt of Jupiter's dipole is about 10 degrees. It's similar to the Earth. And as Jerry remarks here, one important consequence of this, of course, is that when Jupiter is spinning about its axis, the magnetic field is doing this. And of course, that means that if you're a satellite out here, you see a time-varying magnetic field, and that time-varying magnetic field will induce currents in you if you have a conducting region. And this, of course, is the way, this was the way we decided that Europa has an ocean of salty water, likewise Callisto, and actually Ganymede too, although Ganymede, of course, has a dynamo, so it's more difficult to separate it out. The same thing cannot be said for Saturn, and this is interesting. So here's the corresponding map for Saturn, and you'll notice two things. First is that it's actually symmetric, and the second is that the fields are substantially smaller, even though we think that Saturn is rather similar to Jupiter. It's true that you have to go deeper into Saturn before you get to a conductor, and so by the inverse cube of the dipole field, you're not going to have as big a surface field, but actually that's not enough to explain this smallness of Saturn's field, which is only 0.2 Gauss. It's only about half Earth's magnetic field at the surface. And perhaps that is because there are zonal flows inside Saturn that are modifying the magnetic field. Turns out that can promote axisymmetry. Could be the same mechanism even as the one for Mercury. Of course, the field cannot be perfectly axisymmetric, and you would hope that the Cassini spacecraft in the period at the end of its mission will actually see the non-axisymmetry and perhaps even determine the rotation rate, because at the moment we're not even certain what the rotation rate is, because the way you get the rotation rate of fluid planets is by looking at the magnetic field, and that only works if the field is tilted. So in the case of Jupiter, of course, we have spectacularly accurate rotation rate to within 0.1 seconds. In the case of Saturn, it's uncertain to 10 minutes. And finally, we come to the magnetic fields of Uranus and Neptune, and as you can see in these maps, they're very different indeed, although they're kind of similar to each other. Obviously not in the sense of overlaying them. You wouldn't expect to be able to do that because there's nothing special about the coordinate system. But you can see that there's a similar complexity, and this complexity is expressed in the fact that Uranus and Neptune do not really have dipole-dominated magnetic fields. They're actually quadrupole family fields, and there are two aspects to that kind of magnetic field. One is that they have a large quadrupole moment. The other is that the ratio, so that means the ratio of quadrupole to dipole is large. The other is that the dipole part of it has a very large tilt, which is actually, in terms of spherical harmonics, what we mean by quadrupole family. The way you express that in terms of spherical harmonics is whether L plus M is even or odd. Well, L is 1 for a dipole, M equals 1 for an equatorial dipole, L equals 2 for an axial quadrupole, and so on. These planets do not have, we think, metallic hydrogen. It's unlikely that the conductor in this case is hydrogen. It's more likely to be a water-dominated material, and we know from shockwave experiments that if you shock water to high pressure, then you get conduction because of the mobility of the protons. So this is likely to be protonic conduction, and that's an indication, by the way, that you really don't need a really good metal. It can be good enough to have a good ionic conductor. So let's finish then with some concluding thoughts. First, the importance of using magnetic fields to understand the interior. It is a window to the interior structure and to interior dynamics. But this whole field presents us with a problem. We don't really understand yet in a predictive way whether a planet should have a magnetic field or not, and I will deal with that in more detail in the second talk. But this is a major challenge. And of course, you would hope also to make connection to understanding the magnetic field of the Earth. So what I'm going to do now is pause, and if there are any questions just about the observations, I will talk more about theoretical interpretation in the second talk, but I will happily take on any questions at this moment about the observations.